RTMaps 让你的机器人系统从 Perception 感知开始就赢在起跑点。以自驾车系统的组成为例，刚开始的非同步系统，因为不同感测器的取样频率、取样大小、传输协定等不同因素，传数据应该都是时间不同步，因此 Perception 感知时，数据需要经过及时的处理及融合，让其同步后，方能后续给同步系统经演算法或模型分析，做出运动控制的决策。这也是 RTMaps Real-Time Multisensor Application 的含义。RTMaps 不只做时间同步、资料融合，它也是 End-to-End 软体整合解决方案。机器人系统从开始数据的来源，包含实体数据加虚拟模拟的数据，之后对这些非同步数据做即时处理，再经过 AI 赋能的演算法的判断推理。演算法呢支持 ROS、C++、Python、MATLAB、Simulink， 最后还可以部署到边缘运算或 IoT 平台上。RTMaps 是 DSpace 旗下的 Intempora 公司研发。DSpace 是全球在工程模拟及验证领域解决方案的技术领导者。他们提供了这一系列的 YouTube 课程，让你可以初步认识 RTMaps 软体的强大功能。浩进公司是 DSpace 台湾代理商，如您有产品或专案的需求，欢迎与浩进联络。你也可以索取 RTMaps 试用版，对于学生则有提供1年的免费试用。
Hello, welcome to this tutorial. We will learn how to work with CAN buses in RTMaps. First of all, let's start with a CAN stream source. We will start with a recorded dataset. Just drag and drop a .rec file on the current diagram. This creates a player component that exposes a number of sensor streams. For display purposes, let's add an image viewer component to visualize the front camera. On the vehicle CAN output is our CAN frames stream. Instantiate a CAN frames viewer component to display the raw frames. After starting the diagram execution, we can see that the front camera and vehicle CAN bus streams are played back. Now let's see how to decode the CAN data. We need an RTMaps package called RTMaps CAN processing.pck. It contains the CAN Decoder component which we add on our diagram. This component accepts CAN frames on its input, and requires a .dbc file in its database property. The CAN decoder then creates the outputs corresponding to the messages and signals described in the .dbc file. Selection property allows to reduce the number of outputs and to keep only a subset of the available signals using a standard regular expression. Let's keep only the signals which full name contain keywords, vehicle, or control, for instance. Display some of these signals with various widgets such as the vehicle speed in a gauge, lateral acceleration and yaw rate in a scope, brake pedal state in a lamp widget. Since the output was filtered out, we can retrieve it by adjusting the selection property. Let's start the execution and organize a little bit our windows. The CAN frames are decoded and signals are displayed synchronized with the video stream and all other sensors. Adjusting the scope scales. Driver has pressed the brake. We can always rename the widget titles. We could also connect these CAN signals outputs to any kind of processing and data fusion components, of course. Now we will learn how to connect to a physical CAN bus for data acquisition and command control. Let's first remove the player component from the diagram. RTMaps supports a number of CAN interfaces from various providers such as Vector, Peak Systems, DSpace, Kvaser, Star Cooperation, or any socket CAN compliant device on Linux systems. For this demo, we'll use a Kvaser interface. Let's register the RTMaps CAN kvaser.pck package, then add a Kvaser interface component on the diagram. Configure it with a channel number, the CAN bus baud rate, etc. This way, we get our CAN frames acquired from the bus, and we can connect this stream to the CAN decoder. And the CAN frames viewer components. This video is not shot on a real vehicle, but a CAN cable is connecting two channels on the laptop as a loop. We can hence create a second Kvaser interface component, configured for channel 1, that will be able to publish CAN frames on the bus. These CAN frames will therefore be acquired on channel 0. We then need to publish CAN frames to this new component input. Let's use a CAN Encoder component which can generate CAN frames out of various signals, the opposite of a CAN decoder. Provide it with a .dbc file, likely the same as for the CAN decoder, so the CAN frame IDs and signals match. Then feed its inputs with signals that we will generate here using input widget, such as knobs. Let's build a bar with 3 knobs. One can see that the CAN encoder inputs don't light up when dragging connections from the knob outputs. This is due to a data type mismatch. We can check this. The knob outputs provide 32-bit floats while the CAN encoder inputs we need accept only 64-bit floats. Let's use a number converter to cast the data to the right data types. Now we can connect to our 3 signals: transversal acceleration, yaw rate and vehicle speed. We can as well use a by state button to feed the brake pedal state input. Last but not least, we uncheck the wait for message completion property of the CAN encoder. Otherwise, the encoder would wait for reception of new data samples on each input used to generate a given CAN message, in order to build complete CAN frames. For our demo, we didn't connect all the inputs for our messages. Therefore, we tell the component that it can generate incomplete messages. Remaining signals will be filled with zeros. As a summary, we get signals from whatever components, other sensors, processing component or like here, input widgets. We encode CAN frames based on these signals, publish the frames on a physical CAN bus. Acquire them in parallel via a different channel as if they would come from the vehicle, decode the acquired frame, and display the decoded signals. We can now verify that the actions on the input widgets go through the entire data flow to the corresponding display widgets, via a physical CAN bus. Hope you enjoyed. See you soon for more RTMaps tutorials.